Hello, and thank you for joining us today. My name is Arij Al-Zubaidi, Content Marketing Executive at Erlang Solutions. Today we're thrilled to be joined by guest speaker Jack Vanlightly, author of the popular RabbitMQ versus Kafka blog series. Jack is a software architect based in Barcelona, specialising in event-driven architectures, data processing pipelines, and data stores, both relational and non-relational. This webinar is the first in a series of 3 in partnership between Jack and Erlang Solutions, highlighting the differences between RabbitMQ and Apache Kafka. Before we get started, we'd love to hear from you. You can tweet us using the hashtag Erlang Solutions Talks or submit a question for the Q&A with Jack using the questions box on the platform. As a reminder, a recording of the webinar and the slides will be shared after the webinar has ended. Please keep in mind that this is a live event and that we may experience some technical issues, although hopefully not today. Now let's get started. Over to you, Jack.
Hi, good afternoon. Today we're going to look at RabbitMQ and Apache Kafka from an event-driven architecture perspective. We'll look at the core concepts regarding each one, and then we're going to build out a few topologies and compare them. We'll try to gain some insights into when one or the other better fits your needs. In a future webinar, we'll be looking deeper into delivery guarantees, ordering guarantees, scalability, and high availability features. So my name is Jack Vanlightly. I'm software architect of Concatel here in Barcelona. I do mostly event-driven architectures, various messaging systems, data integrations. You can read my blog to see the kind of work that I do. So basically, at the core of each platform is a data structure. RabbitMQ uses the queue and Kafka uses the log. This choice of data structure fundamentally affects the design and capabilities of each system. So a queue is a first in, first out data structure where we write to a tail and we read from the head. Data is transient in nature. The very reading of messages removes them from the queue. That means we cannot share a queue between applications, for example, a billing and a notification system, because they would be competing for the same messages. That means that queues are per application. Whereas a log, also known as a write-ahead log, transaction log, commit log, is append only, ordered by time. Each item has a log sequence number that identifies its position in the log. Data is persistent in nature. So we can have multiple readers reading from different points in the log, each without removing the data and without affecting each other. So let's have a look at the building blocks of RabbitMQ, which is all about routing through exchanges and consumption through queues and consumers, and some extra things like deadless exchanges, alternate exchanges, and virtual hosts. So at the core is exchanges, queues, and bindings. Publishers send messages to exchanges, and consumers read messages from queues. And in between, we have bindings. Now, queues can bind themselves to exchanges, and that way we can do routing from exchange to queue. But the publisher and the consumer are quite abstracted from one another, the publisher publishing to one endpoint and the consumer consuming from something else. And that gives us quite powerful and evolvable architecture with RabbitMQ. So the simple topology is a publish subscribe one. We have one example of an exchange is the Fanout exchange. This simply does a broadcast of each message to each bound queue. So in this case, each of the 3 queues will receive every single message, which means that the consumers are not competing for messages, they each receive everything. We can do some more clever routing by routing keys. So a routing key is put on a message by the publisher. The direct exchange basically does an exact match between a routing key and a binding key. So when a queue binds itself to an exchange, it can put a binding key. And then the exchange will route according to that key. So we see here QA will receive the created routing key, QB modified, and QC cancelled. We can get a bit more clever than that by using the topic exchange, where we leverage wildcards. Now, each routing key is made of multiple words separated by dots. And the wildcards we get match a single word with a star, or we can match multiple words with a hash. So in this example, we can route all messages which have a routing key of booking dot something to queue A. Queue B expects a 3-worded routing key where passenger is the middle word, and queue C does an exact match on payment received. We also have a header exchange. This is a very powerful exchange where we can route based on message headers. Publishers can add custom message headers, and the queues can bind to a header exchange and define which message headers they are interested in. And they can also say whether they should all match or any should match. But we can do routing based on multiple different headers. The only downside of the header exchange is that it is quite slow, can use a lot of CPU, and so does not scale particularly well. So a default exchange is not an exchange type, it is simply a direct exchange, but it is created in every virtual host. So virtual hosts we're going to look at a little bit later. But basically, the default exchange allows us to do point-to-point messaging. So how it works is a publisher puts the routing key as the name of the queue that it wants to receive the message. And this guarantees that a message will be sent to only one queue and by name. We can protect against routing failures with an alternate exchange. Again, it's not an exchange type, it's just a configured relationship between two exchanges. This can be useful for, if a publisher might put a routing key that we don't support, or maybe a problem in the topology. And there's even some very clever uses of alternate exchanges to perform some clever routing. Now, with any messaging system, we have the concept of competing consumers and non-competing consumers. So a competing consumer is one where they compete for the same messages of a given queue. So in the top example, we see the Fanout exchange we saw before, and we have 3 different queues and 3 different consumers, and they do not compete. Each one receives every message. But a simple way of scaling out consumer is just to simply add more of them and just consume from the same queue. So that's what we see below, and we see the shipping service is now consuming, sharing about 1/3 of the messages go to each consumer if they all consume at the same rate. Now, there are downsides of competing consumers against a single queue, because we can then process messages out of order when they're very close to each other. When we have like a queue, it's like a linearized set of events, but as soon as you parallelize that, you lose ordering guarantees. So one other thing is we can actually reach the limit of a queue. So a queue is an Erlang process, and so it has a limit of how far it will scale. So what we can do is we can scale out the queues, and we could scale out our shipping queue into 3. And then we can put a random exchange in front of it, and the random exchange simply load balances randomly across the 3 queues. But again, here we lose any ordering guarantees, because depending on the speed of each consumer, maybe one restarts, we can be processing things out of order. But we can have a way of scaling out while maintaining message ordering. So with a consistent hashing exchange, we can actually run a hash function over a routing key or a message header or a message property, and each queue that is bound to the hashing function, we can define an amount of hash space. So in this case, we say that each one is responsible for 1/3 of the hash space. And it basically means that if we've got, for example, message headers with the customer ID, customer 1 would always go to the same queue, perhaps queue 2. Customer 2 would always go to the same queue. And so then we still get the linearized set of events in the same queue, and we can guarantee order processing while also scaling out. There is also a sharding plugin. So this is one of the ways where we can add extra functionality to RabbitMQ. The sharding plugin ships with RabbitMQ, but you have to enable it. And we can use it with the modulus exchange. So this is a similar exchange to the consistent hashing exchange. It uses a slightly more simple hashing function, but it allows us to, again, distribute messages across queues, but in a way that messages of the same routing key always go to the same queue. And with the sharding plugin, it also auto creates our queues for us and can even replicate those queues across multiple nodes. We can apply queue limits. We can limit the length, that is the number of messages in a queue. We can limit the size in bytes of a queue, and we can apply time limits. The publisher can put a time limit on the message. So each message could, in theory, have a different time limit. Or we can put a TTL on the queue itself, and that means every message in the queue has a time to live that's the same. So what happens when a new message arrives at a queue that is full? Well, the new message gets added to the queue successfully, but it ejects one message from the head. So it favors new messages over the older messages. Likewise, if there is a message that has reached its TTL limit, if it's in the middle of the queue, it stays there. It can only be removed once it reaches the head. So RabbitMQ does respect the kind of fundamental concept of a queue, that it can only remove items from the head. So if you don't want to lose these messages when they get ejected, you can set up another exchange, can be any exchange type, and you just say that the dead letter exchange of this queue is this exchange, and then you can bind queues to that exchange, and it means that you can have a place where these messages go so you don't lose them. There are ephemeral queues. We have the auto delete queue, which is where as soon as the last consumer cancels its subscription to the queue, or its connection fails or whatever, once it has no more consumers, it auto deletes itself. There's also queue expiration, where we can set a time limit where once, for example, 5 minutes has passed and there's no more consumers, then it will auto destruct. There are exclusive queues where consumers can declare their own private queue that no one else can connect to, and once their connection closes, the queue is destroyed. And finally, there's an auto delete exchange, which will delete itself once all bound queues have unbound themselves. So we can even create an entire topology based on ephemeral infrastructure, where we have auto delete queues with consumers consuming from those queues. Once the consumers stop consuming, the queues delete themselves, and now the auto delete exchange deletes itself and everything's gone. There are lazy queues. So these are memory optimized queues. When you have very long queues, we don't want to maintain the whole thing in memory. So with a lazy queue, messages are aggressively written to disk, and then they're only loaded back into memory on demand when consumers need them. And there are priority queues. So this is no longer FIFO. It's the publisher sets the priority on each message, and they get delivered in that order. Not a great feature. I've never used them. I find that some of the drawbacks are a bit too problematic. So some of the drawbacks are that if you've got quite a lot of higher priority messages, then low priority messages can get stuck. And also, if your queue fills up, then your high priority messages will be at the head of the queue, and so a low priority message that comes in will eject a high priority message. So it's in general better to just separate queues into kind of few different priorities. And finally, there are virtual hosts. So this allows a limited set of multi-tenant architecture. We get some isolation between exchanges, queues, and users. We cannot route between the two virtual hosts. It does not give us resource isolation, so it's not sort of bulletproof multi-tenant architecture, but it can be quite useful. Okay, so let's have a look at Kafka building blocks. And after this, we're going to start building some topologies, and then we'll start getting more of an idea of what all this means. So Kafka is a distributed, partitioned, replicated commit log. So distributed because it's deployed as a cluster of nodes, just like RabbitMQ often is. It's partitioned because each topic can be sharded into multiple partitions, and each partition stores a separate set of the data. Each partition can be replicated multiple times to give resiliency, and it's a commit log because each partition is an append-only log. So we have a simple publish-subscribe model here, where the producer sends messages to a topic and the consumer reads from the topic. Here we don't get some coupling of producer and consumer because we produce through a topic and consume from a topic, whereas with RabbitMQ, we have a bit more abstraction between exchanges and queues. So each topic has multiple partitions, and this allows for us to scale out. It's basically a scaling feature of Kafka. So this is an example of where we have a producer and it produces messages to a single topic, and that topic is comprised of 3 partitions, okay? And we also have a consumer group. So a consumer group can be thought of like an application, and the consumers in that consumer group can be thought of as the instances of that application. So this, for example, could be a notification application, which has been scaled out to 3 hosts, and we have each consumer consuming 1 partition. Kafka limits us to 1 partition can only be consumed by 1 consumer per consumer group. Okay, so that means that the unit of parallelism is the partition. We cannot have more consumers than partitions. So we have to be scaling out our partitions in order to scale out and increase our scalability. So if we add more consumers, then the consumers will sit idle until another consumer, for example, fails, and it can take its place. Kafka does automatic assignment of partitions. And so when there are any changes in partitions or changes in consumers, there's something called rebalancing, and that is where consumers automatically get reassigned partitions, so there's equal distribution. And this is a really nice feature of Kafka because it allows us to seamlessly add partitions and add consumers and remove consumers without having to sort of manually work out how we distribute the load between those consumers. And this is something that RabbitMQ does not have by default. We don't have to have as many consumers as partitions. We could have a single consumer, or in this case, we have 3 consumers consuming from 5 partitions. And the consumer group, the sort of partition assignment logic automatically works out who gets assigned what. Now, there's some things to be careful of when we work with partitions, especially if we're using message keys for distribution. So there's 2 ways of distributing messages between partitions, and it's chosen by the producer. So the producer can decide to do round robin, but there we lose message ordering guarantees because we only get ordering guarantees at the partition level. There is no way of maintaining some global ordering of events across all partitions. So the partition is where we get ordering. So quite a common thing to do is when you do care about ordering guarantees is that we do something similar to RabbitMQ with a consistent hashing exchange, where we actually hash the message key and choose the partition based on that. And that means that, for example, customer 1 always goes to partition 2. But when we change the partitions, that will change the hash space that each partition is responsible for. And so we can end up in 2 different partitions having the same customer. So some care does need to be taken around partitions. Here we see that we have 2 consumer groups. So this could be, for example, our notification service and our billing service. As we can see, partition 1 is now consumed by 2 consumers, but they are of different consumer groups, and that's fine. We just can't have 2 consumers of the same group consuming from the same partition. So producers append messages to the end of partitions, and the partition is chosen by round robin or partition key. Data is not removed upon reading, it is removed by a data retention policy. This is often a time window or the size of the partition. There is also log compaction, and we'll be looking at that a little bit later. Now, consumers need to track where they are in the log, because with RabbitMQ, they're just being delivered messages in a stream. But with Kafka, consumers are pulling messages in batches from the log, and each consumer can be at a different point in the log. So they need to track where they are in that log, and their position is called the offset. And what they do is every time they are ready, they've processed a batch of messages, they commit their current offset. And then next time they start reading, they can read from that offset. So here's just an example of the 3 partitions and the producer appending messages to the end of each partition. We have the 2 consumer groups and the 3 consumers. Each consumer can be reading at a different offset, and that's fine. They're completely independent. So partitions is one way that Kafka scales so well, and another is that it leverages batching. So one of the benefits of batching is that we can get much better compression. So compressing a batch of messages is much more efficient. We can get much smaller message final sort of size in bytes than if we compress every message individually. And so what producers normally do is they are in a sort of time window of a few seconds, they accumulate a batch of messages and then they send them out to each partition. Okay, log compaction. So this is a really nice feature that other log-based messaging systems don't have. And what it does is it is used to clean up old versions of a given record or message, and it uses the message key. And so you end up only keeping the latest version. So it's a periodic process, and what it will do is it will go through the log tail, and the tail in this case is defined by you. You can say that the log head is defined as the last 24 hours, and everything else can be compacted. And what it will do here, we have, for example, all these letters represent a record key. And what it will do is it will look for all the older versions of that record and simply remove them. This can work really well. This only really works if you store the entire state of an object in the event. So if you're using, if you're sending deltas or differentials, then you're going to lose important information. But if, for example, every time we change a booking, we're always sending the complete state of that booking, then we can eliminate older versions of that booking without a problem, and then we always have the latest snapshot of the data. It also means that our partitions don't grow too big. We can keep data for much longer. So another really neat feature of Kafka is the schema registry. Versioning of messages in event-driven architectures can be painful. Okay, so different consumers might update at different times, and the publishers can be updating at different times, and we need to make sure that everyone stays compatible and there aren't any outages because we've updated a message sort of structure and now a consumer doesn't know how to read it. So the way Kafka solves this problem is through the schema registry, and it uses Avro, which is a compact binary serialization format. And so it's extremely compact, similar to proto buffers, except that with Avro, you need the schema. So a consumer cannot read an Avro message unless it knows the schema. So the schema registry is a very simple service, which you deploy next to your Kafka cluster, and producers send their schemas to the registry and consumers get the schemas, and the schema ID goes in the message. This is all transparent to you. It's all integrated into the client libraries. But another thing that's really cool about Avro is it has a very nice way of controlling backwards compatibility and forwards compatibility. And so you can actually ensure that you don't make break-in changes in your system. And finally, we can't really ignore all the data analytics and all the data replication and migration products and ecosystem. Although they don't form part of an event-driven architecture per se. And when I talk about event-driven architecture, I'm talking about domain events. Okay, so but one of the benefits of Kafka is it has a very developed ecosystem around these data analytics, and every topic that you have is potentially a source for your analytics systems to tap into real-time data. And there's Kafka Connect, which is an open source set of connectors. We have sources and sinks. So a source is able to read data from a data source like Postgres or Elasticsearch or whatever, and it can post the data in real time to a Kafka topic. And we have sinks, which are able to read from Kafka topics and then write that data to data source, pretty much the similar set, Spark and Redshift, SQL Server, Postgres. And it is a really nice way of sort of plug and play. You don't need to develop your own sort of ETLs with custom code. You can just use the Kafka Connect open source tools. Okay, so enough of the building blocks. Now we're actually going to build something. and we're going to compare, sort of get to see how the exchanges and the topics kind of look. So we have an example scenario where we have 4 applications. Okay, we have an e-commerce site, we have a sales and inventory service, a billing service, and a shipping service. And we have 3 event flows. So the e-commerce site can place an order, and that's a request that goes to sales and inventory, that then places the order and emits an order placed event. The billing service then can bill the client, and once billed, it will emit an order billed event. Now, the shipping service, as soon as it receives an order placed, can start preparing the shipment and getting it all ready. And then once it's received the order billed event, it will ship. Likewise, with modify order, if the shipping service has not shipped the order, it can just modify the order in place and wait for the modification build event before shipping. Or if the shipment's already gone, it can prepare a new shipment and wait for the billing to occur. And we have a cancel order where the billing just needs to refund the client and the shipping needs to cancel the shipment if it hasn't already done so. But the shipping application does not care about the refund event because it just needs to cancel the shipment. So there are, of course, many ways of doing that with RabbitMQ, but this is one example where we use Fanout exchanges per event. So this is kind of mimicking a common pattern we see with other messaging systems based on queues, which use topics. So these are kind of like a topic per event. And then the sales application has a single queue, and it binds its queue to all 3 of those events. So why a single queue? That is because we want relative ordering of events. We could have 3 different queues, one for each of these events. But the trouble is that the place order request is probably going to be high volume, and the cancel order probably is much lower volume. And at any point, if the place order queue filled up, then we could end up trying to process the cancellation order before we've even done the place order. So as your topologies get more and more complex, we really need to linearize our events as best as possible and get ordering of related events. And so feeding into a single queue can do that for us. Now, of course, this doesn't scale, and we'll be looking into that in the next slide. So the sales application can then publish its events, again, to event-based Fanout exchanges, and both the billing and the shipping queues subscribe to both because they're both interested in all 3. And the billing service emits an order refunded, order billed, and modification billed. And the shipping only cares about order billed and modification billed, and it has its queue bound to those 2. So the shipping queue has bound itself to 5 Fanout exchanges. And that basically gives us exactly what we want. Now, having a single instance of an application and a single queue might not scale. So you might be tempted to scale out your sales service, for example, and have 3 or 4 or 5 copies all reading from the same queue. This could work, but you do introduce some possibility of out of order processing, because now you're parallelizing a single sequence of data. And so there is some risk that you can process out of order. That might be okay for you. You might be able to live with that risk, or you may not. If you want to be guaranteeing relative ordering of your various related events, well, you could actually scale out your queue. Here we've scaled out our queue to 5 queues, and we've put a sales hashing exchange, a consistent hashing exchange, in between our 3 Fanout exchanges and our queues. And that way, when the e-commerce site, as long as it puts the order ID as either the routing key or a message header, we can then configure our exchange to route by that and make sure that for a given order, it always goes to the same queue. And then as long as we have 1 instance of our sales application per queue, we guarantee that we process these events in the right order, and we get scaling. Okay, let's have a look using topics. So in this example, we don't have lots and lots of exchanges. We have 1, and it's the topic exchange that comes with every virtual host, the amq.topic. And so every single message gets sent to that exchange. So what we do now is we put a routing key to say what type of event it is. And then we can use binding keys on our queues to say which ones we want. And so the sales queue says it wants place.order and modify.order and cancel.order. Billing wants order placed, order modified, and order cancelled. And so essentially we get the same behavior, but with quite a different topology. Okay, let's have a look at Kafka. So again, relative ordering, ordering of related events is important, because in this kind of architecture, we are very interested in maintaining data consistency. Imagine you had a database where you did a bunch of reads and writes, inserts, updates, deletes, but the database couldn't guarantee that it would do them in the right order that you said. It wouldn't be very useful. And so you can think of that with a messaging system as well, especially in this kind of context. With your data analytics pipelines, we don't care so much about the relative ordering because we're doing aggregations and counts and things. It doesn't really matter so much. But with this kind of architecture, we really do care about the ordering of related events. So in this example, we have one topic for all our requests. So we get the nice ordering there. And then the sales application publishes its 3 events to the orders topic, and the other 2 services publish all their events to the orders topic. Now, the nice thing about this is that we get this kind of global ordering of our order events. We can guarantee that for every single type of event related to a given order, it is logged in the correct order. The downsides are that the billing service is now having to read messages it doesn't care about. But reading messages from Kafka is cheap, and ignoring messages isn't too bad. So it is a valid technique to do that. Where it might not work is if you've got some events that kind of dominate with a very high message rate, and you might have a few other messages that have a very low rate. And if you have a consumer that only wants a low rate event, then you're having to forcing it to scale out just to be able to read these relatively few events. So in that case, you might want to degroup it a bit like this. So we could decide that actually, do you know what? We can still maintain our ordering of related events, but still split it out a bit. So here we have an orders topic and a billing topic and a shipments topic. And so we still keep the ordering guarantees that we want, but now we're not forcing applications to read so many messages that they don't care about. Right, and you could go for a topic per event. Now, this might be great for your data analytics pipeline, where you could have high volume and you don't want to have to read messages that you don't want to consume. But now you could get some pretty undefined behavior whenever you get some high load, or one application restarts and the log backs up a bit. We could start processing things out of order, and then it's very difficult to recover from that. So although you can do it, I don't recommend it for this kind of architecture. Right, let's modify it a bit. We're going to add a class of service. So we've got some customers who are very important to us. So they get a priority processing. So fast tracks throughout the system, throughout all the applications. They all need to prioritize the processing of priority orders, and even standard customers can pay more and get a priority order as well. So we only care about this with regard to placing orders and modifying orders. So with RabbitMQ, we could swap our well, I've actually put topic exchange here, but it's a direct exchange. So we can swap our Fanout exchanges for direct exchanges, and we can split our queues into 2 and have a priority queue and a standard queue. And the e-commerce site now puts a routing key of priority or standard. So that means that with our sales priority queue, we have a binding key of priority, and the sales standard queue has a binding key of standard, and they both bind to all 3 exchanges. And basically that means that they only get the priority messages that they want. Now, and here I've got it going into a single sales application. You can probably want to split that in 2 as well, and have a sales priority service and a sales standard service, and assign different infrastructure. It really depends on how far you want to go with the fast tracking. And the sales application again will maintain the class of service. It will put the class of service in a routing key, and again all the other queues will be doing their binding based on that routing key. or we can do it with topic exchanges. So it starts getting quite busy, this diagram. I've gone for two-tiered layer of topic exchanges. You could do it with a single one and just have many bindings to a single topic exchange, or you can do it like this and have two tiers. So now the e-commerce site, and in fact every publisher, is appending the priority to the routing key. And then the first topic will send out the messages, will route them to the 3 topic exchanges based on their bindings. So the sales topic exchange wants anything that's place.order.star, modify order.star, or cancel order.star, where star represents priority or standard. And then the sales priority queue and the sales standard queue is trusting the sales topic to be configured correctly and says, yeah, I don't care anything, I just want to know that it's a priority message or a standard message. And that's how it works for the other queues as well. And so that's just a way of doing exactly the same thing, but with two-layered topics. We could even do the same thing again, but with a header exchange. So we don't put the routing key, we don't put the priority in the routing key, we now put it as a message header. And then we just use a header exchange to route based on a message header. So it looks very similar. And another way of doing it with RabbitMQ would to use 2 different virtual hosts. So we could create exactly the same topology in 2 different virtual hosts with 2 sets of applications. And we could even take it further than virtual hosts. We could even take different clusters of RabbitMQ. And the e-commerce site can simply send to one virtual host or the other, depending on the priority. So how can we do this with Kafka? So one way would be to not change the topics at all, but to split out the applications and have a priority and a standard application. And reading messages from Kafka is cheap, and each application reads the whole topic, and it just ignores the messages that are not of the class of service that it wants. Again, we are reading messages that ultimately we don't do anything with, but one thing also to take into account with Kafka is you might choose Kafka because of the ecosystem for data replication to other systems, to data analytics, and those systems might not care about class of service, and it might be quite nice if they could just consume from a topic without having to go to 2. Now we could do 2. Here we basically split it in 2, where we have a priority set of topics and applications, and we have a standard set of topics and applications. So the e-commerce site has to decide which topic it's going to send it to. Now, the only downside of this one is that if you have plugged in any ETLs and data analytics systems, then now they have to go to 2 instead of the 1. So yeah, again, just to reiterate, any topic with Kafka is a source for real-time data for other systems. Now, you can do that with RabbitMQ, and there's no reason why we can't. You can plug in, very easily to any exchange, add another queue, and that's fine. It's one of the great things about RabbitMQ is that, we can just plug in any more queues we want, and that's great. But the ecosystem around, data replication and things like that are not as developed in RabbitMQ as they are with Kafka. Okay, so some final insights. We get 2 types of decoupling. So with RabbitMQ, the endpoint we publish to is decoupled from the endpoint we consume from. So that means that we can have a set of, for example, topic exchanges, which are a group of Fanout exchanges for each event. And that's it. And then each application can create its own queues, its own routing that it wants, and we can add applications. Each application has the power to mix various related events into its queue and maintain message ordering. And it's very flexible. We can, an application can change what it consumes without affecting any other application. Whereas with Kafka, the endpoint we publish to is the same as we subscribe from. Topics in Kafka are shared infrastructure. We cannot optimize a topic for a given application. With RabbitMQ, we can just optimize. Each application can create the routine at once and optimize that for itself. But with Kafka, everything is shared. So the decisions we make are at more of a global architectural level, and we have to think very carefully. And then changing that can be painful because if we decide that we want to group more events into a given topic or change to group less into a given topic, there are a lot of systems that are affected that need to change with it, especially given Kafka is very persistent in nature and may have data going back a fair amount of time. That's a lot of data that we need to now work out if we want to move it, or it can just be quite painful. Now, with the temporal decoupling, RabbitMQ, the consumers read the message once, most likely close to the time of publishing, whereas with Kafka, we're much more decoupled temporally from the publisher. We can read a message multiple times. In the end, it's just an offset, which we can change, and we can go back in time and read again. If a developer puts a bug in an application, and we're doing some processing wrong for 24 hours, then we can just set the offset back 24 hours and read the messages again. That's much harder to do with RabbitMQ. You'd have to somehow republish the messages if you could at all. And so we could even develop a new application, and it could go back and read messages from before that application was even developed, with Kafka, depending on how you manage your data and how long you keep the data. And that's where log compaction can help. So finally, they both do simple pub/sub pretty well. And whether you're looking to choose one or the other really comes down to some of these points. So with RabbitMQ, we really do have an easily evolvable topology. One application can choose to mix in 5 events to its queue, or 2, or whatever. It can do what it wants, and it does not affect the rest of the topology. Whereas with Kafka, we have to think very hard about our topics and design it well, taking into account all the applications that will consume it. But with Kafka, we get really simple scaling, where we get nice auto assignment of partitions to consumers, and we get a very developed data replication ecosystem around it. We can go back in time and consume older events. So it really depends on what you want. And I would say that RabbitMQ is just very, very flexible, and Kafka, you get some other benefits like the scaling and the persistence. So that's that. If you got any questions, then now's the time.
Jack, thanks for that very detailed overview of RabbitMQ and Kafka. As Jack said, we'll open the floor to questions shortly, so if you have a question for Jack, please submit them now. First, I'd like to take a moment to tell you about RabbitMQ Summit. 2018 marks the first year of the one-track, one-day conference in London this November. If you'd like to get involved, Call for Talks is now open, as are very early bird tickets at just £150. To learn more, go to rabbitmqsummit.com. Okay, so let's jump into questions. First, from Milan, we have a question. At log compacting, you mentioned that events or messages have versions. Does that mean that I can update events in log?
Okay, so it's an append-only store. So I believe the only thing you can do to update a message is if you want to do what's called tombstoning. And that's where you want to delete a record. Now, because it's immutable, that's a problem. And that could be a big problem now that there's the GDPR coming along. And so, we might have to delete data. And so what Kafka allows you to do, it actually allows you to overwrite a record key with a null, and it will just essentially keep the message there, but it will delete the contents. And if you're using log compaction, you can set it to kind of recover the tombstones, as they're called. But you can't just really update a message in place. It is append-only immutable messages, but you can kind of get a similar thing through log compaction, because if you do send an updated message, then log compaction will remove the old ones. So it is kind of similar to an update.
Okay, thanks for that, Jack. Next question from Matish. Does Kafka have flow control mechanisms similar to RabbitMQ? How does Kafka protect itself from slow consumers?
Okay, so flow control. What's interesting is Kafka can actually do throttling of producers, which is something that RabbitMQ can't really do. I mean, RabbitMQ can throttle basically using TCP, but you can actually use policies in Kafka to actually throttle producers, which is kind of nice. Get protection against slow consumers. I'm not sure. It depends on the data retention policy. I mean, usually people tend to have a decent amount of a few days or weeks. So you tend to have you'd have to be pretty slow, to do that. And basically, once those messages are gone, they're gone. So so if you're slower than the data retention policy, then you'll lose the data.
Okay, thanks for that. We have another question, follow up from Milan. So around log compacting, he's asking, so if we talk in terms of CQRS approach, this compaction is aggregate snapshotting?
Yeah, I guess so. Yeah, I mean, this is, I guess I haven't used CQRS. I mean, I don't know with CQRS if you're really caring about every individual change. I guess with log compaction, you can say, I want all the changes for the last 24 hours, but start compacting after that. But yeah, it's basically you are getting a snapshot. And for your downstream views where you're replicating to some view model, often you don't really care about each individual change. You just want to know what the snapshot is now. So yes, I would say it is. It is used in event store. I don't think it's as fully fledged as some event store alternatives, but it can be used as an event store.
Thanks, Jack. As a reminder, if you have any more questions, please do submit them. On to the next question. Are there any tools to help scaling out queues and performing automatic assignment of queues to consumers like Kafka can do with its partitions?
Right, yeah, so this is one where Kafka does make it a lot easier for you. So RabbitMQ does give you the sort of building blocks for scaling out queues, but you don't get any automatic assignment of queues to consumers. So what you can do is you can go for different strategies. You could, if you've got quite static infrastructure where you've got your named servers, your 5 web servers or whatever, then you can just use your configuration and deployment system to basically make sure that you have each consumer is kind of fixed to consume from a given queue, and scaling out of the queue is relatively fixed. If you have something a bit more dynamic, you could go for, if you're using anything like Docker and Kubernetes, you could even kind of configure each consumer in a separate service, and then configure the service to consume from a given queue or given set of queues. And Kubernetes will then make sure that those consumers stay alive, which is quite nice. And after that, you're getting into a bit more complex territory of using something like Consul or Zookeeper to do some kind of distributed consensus to work out which applications are consuming what. But I don't know of anything out there. It's something you'd have to look into yourself. I've only ever done it through more static infrastructure. So.
Thanks for that, Jack. On to the next question from Thomas. So Thomas says, first of all, I would really like to thank Jack for this presentation. So would I. Thanks, Jack. He has 2 questions. First, will the slides be available? I can answer that question. Yes, they will be, Thomas. You'll be emailed after this presentation, probably tomorrow. And second, how would you solve the need for logging with RabbitMQ?
Well, logging is an easier case. It's a much easier case because we don't really care about event ordering, because you will get that in the log analytics system. We can be sending events a little bit out of order, but we'll still be able to analyze those in the correct order, because we'll be doing some kind of time series or whatever. So it gives us a bit more flexibility with the scaling. So if you've got a lot of data, then you can just be adding competing consumers, and if your queue can keep up, then that's great. I've seen from Pivotal, they're talking about 20,000 messages a second from one queue. I'm not sure about the message size and how that affects it. But RabbitMQ does do quite well with larger messages and scaling. But you can even just use a random exchange and scale out queues and have a bunch of consumers, and even have competing consumers from each of those scaled out queues. And you're going to be losing some of the ordering guarantees. But for basically log shipping, we don't really care about that, because we're going to get that from the analytics system when we're actually reading the data. So I'm not sure if that answers the question.
Thomas, let us know if that answers the question. Thanks, Jack. Next question from Wayne. He asks, what about cluster management? How does Kafka rebalance partitions if one is lost in comparison to how Rabbit manages failing nodes in a mirrored cluster?
Right. Well, we're going to be going into that a bit in the next webinar, but it's a complex topic. So basically, you can imagine you have a bunch of nodes. One node is a controller, and it handles things related to sort of cluster membership for the various nodes. And each partition can be replicated, and we have a leader and follower architecture where basically the followers are periodically getting the latest events from the leader. And so Kafka has what is known as the ISR, which is the in-sync replica list. And so what happens is that when you send a message to Kafka, you can say only respond to say it's been saved when the leader gets it, or when the leader and all the in-sync replicas get it. And so it's a bit complicated to talk about in a short answer, but basically it uses the concept of follower partitions, and they're basically grabbing the latest messages, and they just need to stay in sync. Now, if they fall behind, they get added to this out of synchronization list, and so you can choose as the publisher what kind of consistency you want. It could be that the leader is the only one in sync, and all the followers are a bit behind because of some network latency or garbage collection or whatever. And at that point, Kafka will respond and say, hey, yeah, no problem. The leader and all the in-sync replicas have got it, because there are no in-sync replicas. But as a producer, you can actually say, look, I want to know when all the in-sync replicas have got this message, and they have to have a minimum of 2 replicas, okay? And so that can give you some extra guarantees. So it's pretty tunable whether you want availability or consistency in that way. But yeah, it's hard to really go through it in a few minutes. We'll be into it in more detail in the next one.
Yeah, absolutely. Thanks, Jack. And by the way, the next webinar will be in August this year, and registration will be open from tomorrow as well. Next question from Totvidus. When you need resilient messaging, you can't lose any of the events. How do you ensure this with RabbitMQ, or is it much better to use Kafka in this case?
I would say it depends on your scale. I think Kafka is rock solid under even massive scale. RabbitMQ under pretty massive scale can, I've read here and there that there can be some stability issues. I think Kafka is probably a bit better in this case, but also with Kafka, a lot of it is tuned for scalability, and you have to be really careful, because you can even have the situation where Kafka will say, hey, I've got it, but the way it batches its bytes to disk, if you have catastrophic disk failure, you could actually end up losing it anyway. I mean, they both have the replicas through the queue mirroring with Rabbit, and the leader followers with Kafka, and they both have message acknowledgements where because ultimately it's a chain of trust, it's a chain of responsibility, where there's like a dance where the publisher is handing over the responsibility to the broker, and they have to do this kind of message acknowledgements to make sure that nothing is lost, and the same on the consumer side. And they both have reliable message acknowledgements. They both write to disk. They both replicate messages across multiple nodes. I would say RabbitMQ, you need to be a bit more quite careful, because there are some situations where you can get a split brain, and you can end up having to choose between availability and data loss. So to answer your question, it really depends on your scale, I think. So.
Thanks, Jack.
But
Next question.
Nothing is 100%. Both can lose data. Both can lose data. The fact is if you lose too many nodes, then you can lose data. So.
Thanks, Jack. On to the next question. What supports for client libraries do both platforms offer?
So I would say RabbitMQ has more support for client libraries than Kafka, and it's had that for quite a long time. I think Kafka is catching up. One of my clients, they're primarily a .NET shop, and we evaluated Kafka and RabbitMQ a couple of years ago, and we went with RabbitMQ. One of the reasons was the library support, because a lot of the new features of Kafka haven't got into, for example, the .NET ecosystem. So I think RabbitMQ has the edge there.
Okay, thanks, Jack. Next question from Milan. Can partition be added later in Kafka, and what effect does it have on already stored events? Will they move around partitions?
No, they stay put. So this is where you need to be really careful with your partitioning, especially if you want message ordering guarantees, if you store data for a long time. Because let's say you start off with 10 partitions, and your customer 1 is always going to partition 5. So all of customer 1's events are in partition 5, and that's great. We get message ordering, we get some data locality patterns where that consumer can be computing some statistics and doing sort of locality aware algorithms and things. But then we start growing, and 10 partitions isn't enough, and we need more. So then we add 5 or another 10. Well, the way that the hash space is now distributed among those 20 partitions is different. And so now customer 1 doesn't go to partition 5, it goes to partition 17. And so now we've got messages of customer 1 in partition 5 and partition 17. That's not necessarily a problem for consumers that are up to date. If they're reading the latest data, then that's fine. But if you, I don't know, like another application that's coming online that wants to read the data, or if you've fallen behind a bit due to whatever reason, then you can end up processing the message out of order because it's sitting right there at the start of partition 17 and right at the end of partition 5. So I would recommend that you look at future growth and try and minimize the times you change partitions, because data does not move. And that's true of RabbitMQ as well if you use scaling out queues. But RabbitMQ, the data is transient, so there's not such a long-term issue. I mean, it can still cause the out of order processing though, because data doesn't move, it just changes the new distribution of messages. So
thanks very much for that, Jack. I think that's about as much time as we have today. But Jack, thanks again. And everyone else on the call, this session has been recorded and slides will be sent out tomorrow. So thanks very much, and I hope you can join us for the next in the series. Otherwise, have a good day.
Okay. Well, goodbye, everyone.